Alright guys, we're back at it. So this week we are going to talk about Avogadro's law and then we will get into the ideal gas law. So we've already covered Boyle's and Charles. You did well in your worksheets. Make sure you memorize those equations and the relationships between volume and pressure and volume and temperature. Know what stays constant in each law, and there's one other, well, there's a few other gas laws that we won't be covering, like Gay-Lussac's. We're not talking about that one. Combined gas laws, we're not talking about that one. There's one in your notes, Dalton's partial pressures. All you have to know for that is if you see that they want the total pressure, all you have to do is add up all the partial pressures to get to the total pressure. It's really that easy. So I'm not going to go into detail on that. Avogadro's law, though, I will cover because I don't think the slides are sufficient for the worksheet that I'm going to assign. And so let's jump into this. Avogadro's law. Let me fix this. This is a Visa. Alright, Avogadro's law. This is what typically all your gas equations look like initially. You have these fractions here. So initially it's N1 over V1 equals N2 over V2. And each and every equation that I gave you, I've pre-rearranged for you guys. This is the equation that I want you to memorize. N1 V2 equals N2 V1. Similar to Charles' law with the N1 or the 1 and 2 and 1 and 2 to 1. Like it's similar, just different variables. Here we're dealing with the number of moles, so number of gas particles and volume. And we're exploring the relationship with that. Remember, everything's through the lens of the kinetic theory, and that tells us that we're dealing with gas particles, and temperature affects kinetic energy, which is the rate of speed, which affects pressure because it bounces off the walls of containers, and it also deals with changes the volume. Then if things are speeding up, then they're forcefully hitting against walls and it's expanding and contracting and all these things are going on. And so this theory really makes everything a little bit more clear and helps us understand it, what's going on. Here we're dealing with the relationship between the number of these particles and the volume. So here we go. In this equation, temperature and pressure are constant. They have to stay constant. The relationship between the number of moles and the volume is directly proportional. As you increase the number of gas particles, so the number of moles of gas particles, volume is going to increase. If you reduce the number of particles in a container, volume will decrease. Think of a balloon. You have certain, say it's filled up halfway, you have a certain number of gas particles in this balloon with a certain volume. You blow into the balloon and you expand the balloon, the volume is going to increase, and guess what? There's more air in it now. So there's more number of gas particles in the balloon. They're directly proportional. You release that air, then all that gas particle escapes the balloon. Therefore, the balloon deflates and the volume decreases. That shows the relationship. As one goes down, the other goes down. As one goes up, the other one goes up. In this equation, just like Charles' law, you had to convert the temperature to Kelvin. Here you have to convert mass to moles. So N is number of moles. In some equations you'll see like you'll have 50 grams of oxygen. You have to convert that grams to moles or it's not going to work. If they want your answer in grams, then you have to initially convert grams to moles, and then you take your answer, which will be in moles, you just convert back to grams. And you remember this, how to do this from the stoichiometry mass to mole problems, where we converted it by looking at the periodic table. We looked how much of element weighed in AMUs, we convert that to grams, and then we do some division. So if you have 50 grams of oxygen, we know that oxygen weighs 6, and it's say O2, the diatomic molecule, O2. So that's 2 oxygen. And you have 50 grams of oxygens, and you need to convert that to moles. Remember, oxygen weighs 16 grams. There's 2 oxygens, 32. So you take your 50 grams divided by 32 and you have it in moles. I'll show this on the board, but I'm just helping you understand, like, that's the process you're about to be doing. So let me pause this video and let's show you a practice problem using Avogadro's law. Alright, so here we go. Alright, so here's our practice problem. In a sample of gas, 50 grams of oxygen, O2, gas takes up 48 liters of volume. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. How many grams of gas are now in the container? So here's it wants your answer in grams. So remember, you're always converting to moles, but in this problem you will have to convert back to grams. And in this problem it gives you grams, so we know we are doing conversions. Some problems it will just give you, say it gave you 5 moles of oxygen. Then converting to moles is not necessary, it's already in moles. First step here you have to do is figure out your variables. So I always list them out, N1, V1, N2, V2, and that just kind of like that to keep track of what's going on. So here we have, in a sample of gas, 50 grams of oxygen takes up 48 liters. That's their initial mass and initial volume. So those are your ones. So N1 for right now is 50 grams of O2. Our initial volume here is 48 liters. Okay. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. So now we have a new volume. It increases 79 liters. How many grams of gas are now in the container? So we need to look for N2. So we need to solve for N2. So therefore we need to get N2 by itself here. So to get N2 by itself, all you have to do is divide both sides by V1. This crosses out, and then you get N1 V2 over V1. That's how we're going to solve to get N2. And then you plug in your numbers into the equation, you have your answer. However, we know N equals number of moles, and we don't have moles yet, we have grams. So here we have to convert our grams to moles. So let's start with the 50 grams of oxygen. So I'll do it down here. So we have 50 grams of O2. That's 2 oxygen molecules. And we're converting it to moles. We know for every 1 mole, remember molar mass. If you look at your periodic table, we know the molar mass of oxygen 16 atomic mass units, because the ratios are always the same. The way they developed it, it's 16 grams. So 16 times 2 is 32 grams of oxygen. It's at the bottom. Grams cancel out. They're repeating. That's why I went on the bottom, so we can cancel out grams to get the moles. All you're doing is taking 50 divided by 32. 50 divided by 32 equals 1.6 moles of oxygen. So 1.6 moles of O2. So now N1 now becomes 1.6 moles of O2. Now N2 we don't have to worry about because that's what we're trying to solve for. So here we go. Now you just plug in your numbers into your equation. N1 we now have 1.6 moles times V2, 79 liters, divided by V1, 48 liters. And this will give us our answer. So here we go. We have 1.6 times 79 divided by 48. And we get 2.6 moles. 2.6 moles of O2. So therefore, N2, 2.6 moles O2. There's our answer. Now notice how volume went up, number of moles went up. Stuck with the directly proportional relationship, which is a good sign that we did it correct. It's an easy way to check your answer. Okay, so now we have our 2.6 moles of O2. The question is how many grams of gas are now in the container. So we have our answer in moles. Typically, you can stop there. However, this is a problem that wants to throw every curveball at you. So we got to convert this to grams. And same concept in stoichiometry. Now we're just going from moles to grams. So we have 2.6 moles of O2. We're going to want moles on the bottom here to cancel it out. Moles O2, grams O2. We already know that there's 32 grams of oxygen per mole. And so now all you're doing is doing simple multiplication. You're just taking 2.6 times 32, which is 83.2 grams. And so our final answer in grams, both are correct, but to get the desired unit, our final answer is 83.2 grams of O2. There we go. That's Avogadro's law. Remember, always keep your units the same. So working with volume, if you see one's milliliters and one's liters, you're going to have to do some conversions and make sure they're the same. They always have to line up. It's always got to be both liters, both milliliters, whatever that unit is. It's just remember, it's got to be the same or it's not going to work. All right, there we go.